Google did something in late 2024 that the technology industry is still processing. Their quantum chip Willow did not just set a record or win a benchmark competition. It demonstrated for the first time in history that quantum computers can scale in a way that actually works. That adding more qubits makes the system more powerful and more reliable simultaneously, rather than more powerful and more error-prone. That sounds like an engineering detail. It is not. It is the moment the entire field changed direction. And the conversation about what happens next, the real conversation, not the press release version, is one that almost nobody is having loudly enough. Let us start with what actually broke. For 30 years, quantum computing research operated under a shadow. The theory was extraordinary. The mathematics was compelling. The potential applications were transformative. But the hardware kept running into the same wall. Qubits are fragile, errors accumulate faster than useful computation can occur, and scaling up the system made the problem worse rather than better. Every time researchers built a bigger quantum processor, the errors multiplied along with the qubits. The dream of a fault-tolerant quantum computer, one that could run long enough and cleanly enough to solve real problems, remained perpetually on the horizon, always a decade away, always blocked by this fundamental engineering reality. What Willow broke was that assumption. Google's team demonstrated that their error correction approach crossed a critical threshold where adding more physical qubits to the system actually reduced the error rate exponentially rather than increasing it. Below the threshold, more qubits mean more noise. Above the threshold, more qubits mean more reliability. Willow is above the threshold. This is the first time any quantum processor has demonstrated this property at meaningful scale, and it fundamentally changes what the roadmap to useful quantum computing looks like. The other thing Willow broke was the credibility of the argument that quantum supremacy demonstrations are just cherry-picked benchmarks with no connection to real computational advantage. Willow performed a specific calculation in under 5 minutes that would take the fastest classical supercomputer on Earth, an estimated 10 septillion years. Previous quantum supremacy claims were challenged, and in some cases, partially refuted, when researchers found classical algorithms that performed better on the benchmark problems than initially estimated. The Willow result has proven significantly more robust to those challenges. The combination of a credible supremacy demonstration and a validated error correction threshold makes this announcement categorically different from what came before. Now let us talk about what comes next, because this is where the conversation has been surprisingly shallow. The immediate next step in Google's own roadmap is moving from demonstrating error correction to demonstrating error-corrected logical qubits performing useful computations. Willow has 105 physical qubits. The next generation of Google's quantum processors is expected to scale this significantly, the target that researchers across the field have identified as the threshold for practically useful quantum computation. The point where quantum computers can solve problems that matter in the real world requires fault-tolerant logical qubits, numbering in the hundreds to thousands, which in turn requires physical qubit counts in the hundreds of thousands to millions, depending on the error correction overhead. That sounds like it is very far away. It is closer than it was a year ago because of what Willow demonstrated. The error correction problem was the central obstacle. With that obstacle now shown to be surmountable, the remaining challenges are engineering scale, manufacturing more qubits, maintaining coherence across larger systems, developing the classical control systems needed to manage them. These are hard engineering problems, but they are problems where progress follows investment in time in a more predictable way than fundamental physics challenges do. The timelines being discussed privately inside the quantum computing research community are significantly more aggressive than what appears in public commentary. Multiple researchers who have reviewed the Willow results have indicated that the path to cryptographically relevant quantum computers, machines powerful enough to break current encryption standards, may be measured in years to a decade, rather than the 2 to 3 decades that was the comfortable assumption before this announcement. That is not a consensus view, and there is genuine uncertainty about the timeline, but the direction of the revision is consistent. Willow moved the estimate closer, not further. This brings us to the first thing nobody is talking about loudly enough: the encryption crisis that is already in motion and that Willow just accelerated. Modern encryption protects everything, every online transaction, every private message, every medical record, every government communication, every corporate secret. The security of all of this rests on mathematical problems that are computationally hard for classical computers, primarily the difficulty of factoring large numbers. A quantum computer running Shor's algorithm at sufficient scale could factor these numbers efficiently, rendering current encryption effectively transparent. Here's the part that should concern everyone. An adversary does not need to break encryption in real time to benefit from quantum capability. Nation-state intelligence agencies, and there is documented evidence that several are pursuing this strategy, are engaged in what is called harvest now, decrypt later operations. They are collecting encrypted communications and data today, storing it, and waiting for quantum computers capable of decrypting it to become available. Every sensitive communication sent under current encryption is potentially being archived by adversaries who intend to read it once their quantum capabilities mature. The data being harvested today includes communications that will still be sensitive years from now, military strategies, diplomatic cables, corporate intellectual property, personal financial information, medical records. The harvest is happening regardless of when quantum decryption becomes practical, which means the timeline to practical quantum computing is not just a future technology question, it is a present security question. NIST finalized its first post-quantum cryptographic standards in 2024. These are new encryption algorithms designed to resist attacks from quantum computers. The migration to these standards needs to happen across every system that handles sensitive information. Government systems, financial infrastructure, healthcare networks, corporate communications, consumer applications. This migration is complex, expensive, and time-consuming. It cannot be completed in months. It requires years of coordinated effort across the entire technology ecosystem. Willow's announcement should be the forcing function that converts migration from a planned future project to an active present priority. In most organizations, it has not had that effect. The gap between what the quantum computing research community now believes about timelines and what organizational security planning assumes about timelines is significant and growing. The second thing nobody is discussing adequately is the geopolitical dimension of quantum computing leadership. The United States and China are engaged in a technology competition that encompasses semiconductors, artificial intelligence, and quantum computing simultaneously. China has made quantum computing a stated national strategic priority and has invested billions in research programs, quantum communication networks, and hardware development. The Chinese government has demonstrated quantum satellite communication links, built quantum key distribution networks across significant portions of its territory, and published research indicating significant progress in quantum hardware development. Google's Willow announcement represents a clear current leadership position for the United States in certain aspects of quantum computing, specifically in superconducting qubit systems with demonstrated error correction. But the race is genuinely competitive, and the strategic implications of quantum leadership are profound enough that governments are treating this with the same seriousness they treat nuclear and conventional military capabilities. Quantum computing leadership translates directly into intelligence advantages, the ability to decrypt adversary communications while protecting your own. It translates into scientific advantages, the ability to design new materials, drugs, and technologies faster than competitors. It translates into economic advantages, quantum optimization of logistics, finance, and manufacturing, at scales classical computers cannot achieve. The nation that achieves reliable, large-scale quantum computing first will have advantages across military, economic, and scientific domains simultaneously. The export controls the United States has imposed on semiconductor technology, restricting China's access to advanced chip manufacturing equipment, represent one front of this competition. Quantum computing hardware development is another front, and it is less visible but no less consequential. The third under-discussed implication of Willow is what it means for artificial intelligence development. The current wave of AI, large language models, image generation scientific AI, runs on classical computing hardware, graphics processing units, and specialized AI accelerators performing vast numbers of matrix multiplication operations. This classical AI hardware is approaching physical limits. The energy consumption of large AI training runs is already measured in megawatt hours. The cost of training frontier models is already in the hundreds of millions of dollars. The path to continued AI capability improvement through classical hardware alone is becoming increasingly difficult from energy, cost, and physical constraint perspectives. Quantum computing offers potential pathways that could change this trajectory. Certain machine learning algorithms have quantum variants that run exponentially faster on quantum hardware. Quantum systems may be able to represent and process certain types of high-dimensional data more efficiently than classical neural networks. Quantum optimization could accelerate the training of classical AI models by solving optimization problems that currently require significant computational resources. The intersection of quantum computing and artificial intelligence is one of the most actively researched areas in both fields, and the results being discussed in research circles suggest that quantum acceleration of AI could be one of the most transformative applications of quantum computing once the hardware matures. An AI research community that currently faces hardware and energy constraints could find those constraints dramatically relieved by quantum acceleration. The implications for the pace of AI capability development are significant. The fourth area where the post-Willow conversation is insufficient is drug discovery and material science. Simulating the quantum mechanical behavior of molecules on classical computers requires approximations. These approximations limit the accuracy of drug interaction modeling, material property prediction, and chemical reaction simulation. The consequence is that drug discovery involves enormous amounts of trial and error, synthesizing compounds, testing them, failing, adjusting, trying again. The process takes a decade or more and costs billions of dollars for a single successful drug. Most attempts fail. A quantum computer capable of accurately simulating molecular quantum mechanics without approximation could transform this process. Researchers could model how a drug candidate interacts with a target protein, predict side effects, optimize molecular structure, and identify promising compounds before synthesizing anything physical. The reduction in failed trials and the acceleration of the discovery timeline could translate into both dramatically lower drug development costs and dramatically faster access to new treatments. The same capability applies to materials science, battery technology, solar cell efficiency, superconductor development, semiconductor materials. All of these fields are constrained by the inability to accurately predict material properties from first principles. Quantum simulation of material behavior could enable the design of materials with specific desired properties, rather than the current approach of testing many candidates, hoping to find one that works. These applications require fault-tolerant quantum computers with more capability than Willow currently provides, but Willow's error correction breakthrough is the foundation that makes them achievable rather than theoretical. Where does this leave us right now? The honest answer is at an inflection point whose significance is not yet reflected in public understanding or organizational behavior. Willow demonstrated that the central technical obstacle to scalable quantum computing is surmountable. The roadmap from here to practically useful quantum computing is an engineering challenge rather than a physics mystery. The timeline is uncertain, but has moved meaningfully closer than most organizations are planning for. The things that should be happening now: aggressive migration to post-quantum cryptography, increased investment in quantum research and workforce development, serious policy engagement with the geopolitical dimensions of quantum competition, and planning for the transformative impact on drug discovery, materials science, and artificial intelligence are happening too slowly relative to the pace the technology is demonstrating. Google broke something important with Willow. What they broke was the comfortable assumption that quantum computing is a distant future technology that current planning does not need to account for. It is not distant anymore. The conversation about what comes next needs to become much louder, much faster, and much more specific than it currently is. The organizations, governments, and individuals that understand this earliest will be the ones best positioned for what is coming.